Hi, welcome to Math 150, Section 2, Multivariable Calculus. I'm Professor Miller. If you haven't received an email from me yet, I sent one around 2:30 last night. I just want to make sure that I have you on my email list. So if you haven't gotten an email, please just shoot me an email so I can make sure that you have been added. I, for the most part, do not use the Williams software Glow. I write my HTML code directly and just post all the information there. This way, whenever the college changes whatever system they're using, I can just delete those emails about the retraining sessions. So the web page looks primitive, but it has all the information. I will be posting all of the lectures online. I'm going to be doing something different in this class than I have normally done. So if you could just pass this one down. So how many of you remember high school? All right, how many of you are freshmen? Okay. There should be more hands remembering high school, especially we have this many freshmen. It's not that long ago. But in high school, you meet 5 days a week. And you meet for more weeks than we have. And so the biggest difference between college and high school is we have to move at a much faster pace. We have less time to do examples. And when you get to a class like multivariable calculus, you have more material to do. This all aligns for a disaster. So there's only one way to get through all of this. So I will let you pass this back to her. So what's the only way we can make this work? Or what's the way that you use to make this work in a college class? Yes? Well, that's what we're going to do here, but the standard way is you move at a really fast pace. Or you start cutting material. So how many of you are planning on doing economics? So you want to be able to do things like Lagrange multipliers and optimization. How many of you are planning on doing, say, maybe physics? So you want to do things like Green's theorem, Stokes' theorem. I actually asked this in the first class and I got a yes. How many of you are planning on doing, art? Okay, good, happened again. So we're actually going to talk about applications of multivariable calculus with art. There's a lot of things to cover. And the only way we can do it is either cover the material very rapidly or restructure the way the whole class is done. And so this is the first time I'm doing this. When I taught the class last in 2014, I had a professional recording done of every lecture. We hired a student. We had a high-quality camera that could zoom in, had really good resolution. Much better than the primitive iPad system I'm using now, but this does a pretty good job. What you will be doing in the class is the following. If you elect to do so, which I strongly encourage you to do, you will watch the lecture before class, you will read the material before class, and you will come to class prepared. There'll be a Google Sheets where if you have questions about material or if there's things you want to see, you just put there, hey, Professor Miller, I didn't really understand this proof. I'd really like to see another example on this. I'd like to see an application of this. And this will allow you to control how class is done. This will allow you to personalize your education. This is extremely valuable. How many of you are planning on being professional students for the rest of your life? Okay. That means beyond PhD, that means you do nothing but take classes until you die. So is there anybody who plans on doing nothing but taking classes until you die? Okay, so at some point you're going to want to do things with the material you've learned. In general, unfortunately, you are not going to learn everything you need for the job you need to do. You're going to have to learn new material on the fly. And so a huge part of this class is I want to teach you how to learn. I want to get you to the point where if there's something you don't know, you can pick it up. And that's one of the reasons why I'm trying to structure the class like this. I just had a phone interview for one of my students who was applying for a job. And I basically said, if you want somebody with technical ability, the code monkey from MIT will beat them. They've been doing nothing but coding. They have a better database. But if you want somebody who can learn, this student has demonstrated that she can pick up new material very fast. I've seen her do this multiple times. She may not start off as knowing the most, but within 6 months, if she's like the other Williams students, she'll be at the top of your list. And this is really true. We've seen this with many Williams students over the years, is they have the ability that they can pick up the new information as they need it. So what I will do is 60% of your grade will be being prepared for class, and it will be 92.5. You need to still pass the final to pass the class, but you can have 60% of your grade essentially being an A for coming to class prepared. That means watching the video, reading the book, and posting on the Google Sheet. If you're not sure about something or if there's something you'd like to see, let me know what it is. This will allow us to adjust the class, to go over the examples you want, to go over the applications you want, to really personalize it. You are allowed 3 days when just shit happens and you're not prepared. Right? That sometimes happens. You should try to minimize that. I strongly encourage you to be at least 2 days ahead in the reading and watching, just so that when things happen, you are prepared. Sadly, one of my years in college, one of my 3 mates tried to kill themselves. And all of a sudden, the rest of my semester was very different than what I was expecting, and it was good that I had a strategic reserve in my classes because I had to draw down on it. Things happen to you, to friends, opportunities come up, you want to be prepared. For next year, I encourage you to get some of your books for your classes next year and read the first chapter or 2 over the summer. Put up a little bank. So if you do this, I will give you 60% of the grade as an A. You can have 3 days when something happens. This is different than Professor Miller, we're competing in nationals, and I'm not going to be in class, I'm not going to be prepared. That's different. If you have something like that, that doesn't count towards the 3 days. In terms of lateness policies, if you need an extension for anything, no extensions are granted, except in extreme act of the almighty situation within 24 hours. If you think you're going to be needing an extension, you have to let me know in advance. This is because in the real world, you cannot just say to your boss, 2 hours before the presentation, yeah, I'm not going to be prepared today. You've got to give people enough time to adjust. So if you need to change anything, just let me know at least a day in advance. And usually extensions are no problem. There's going to be a lot of homework. It'll be most every class something will be turned in. We'll have a paper nightmare of sheets coming in and sheets coming back. There'll be lots of review sessions with TAs. We're still working on getting the rooms. So there will be a lot of resources available. There's a lot of material to cover. And the more problems you do, the better it's going to be. So I will put both standard problems as well as some additional extra credit, more challenging problems to think about. I'm a little bit different than most Williams professors in that I don't want to try to get to know you. I will explain what that means. I want you to make me get to know you. When you leave Williams, this is a very special place where you have incredible students, faculty, and staff. And you have incredible access to them. In the real world, it's not going to be like that. You need to make sure the boss knows who you are. In some of my classes, I actually have students write letters of recommendation for each other so that they are aware of what observables are they actually giving. If you make any comments in class, just shoot me an email afterwards. If you could pass that down. Just shoot me an email afterwards so that I can keep a record of what comments you've made in class. This is often extremely useful when I'm writing letters of recommendation. You may think that the comment you made is not that deep or important. Sometimes you're right, sometimes you're wrong, sometimes it actually is a challenging concept. But more than that is I want you to get comfortable speaking. I want you to get comfortable so that when you're in a situation, you can be noticed. When I was an undergraduate, I was terrified to speak in class or to speak in public. And it took me a long time to get to the point where I'm somewhat comfortable speaking out loud. I want to try to have lots of applications of the mathematics here. So the reason I'm wearing this shirt is when I was a very young, newly minted PhD, I got an email that began, "Greetings, my name is David Kelly. I'm a senior criminal investigator at the IRS." And your head just goes down, and you go, "Oh my God, they got me." And and so it took me about 5 minutes before I was comfortable enough to look and read the next line, which was, "I just read with interest your recent paper in Acta Arithmetica." And I was such a young PhD, like, someone's reading my paper? I don't even care that's IRS, someone is reading my work? And so it turns out the mathematics I do is related to detecting tax fraud. And so I want to talk about applications like that. Is how can you use mathematics in meaningful ways like this? I do a lot of sports mathematics, and I have a lot of opportunities for stuff like this. I often have chances for students to do consulting with pay between $20 and $60 an hour. Right now I have several students working with me on a major case for MLB baseball in the multi-millions. And a lot of you already have enough skills. If you can do basic math, basic programming, basic statistics, it's incredible the number of opportunities you have. So if you're looking for stuff like this, including summer jobs or jobs during the semester, let me know. I'm happy to talk to you about different possibilities. I also do a lot of work. I'm an elected official in the Commonwealth of Massachusetts. I'm going to stop sending out more at this point. I am on the regional school committee. And so we had to discuss an effort to regionalize the schools in Williamstown and Lanesboro. And if we use the standard formulas that the state provides, it would cost Williamstown $360,000 and Lanesboro would gain $480,000 for the same level of service. So in any notion of fairness, this should strike you as wrong. If both towns have no service changes, Why should uniting somehow cause? It was the way the states were doing formulas. If we regionalized, they used a different formula and they wouldn't tell us how much money would have gone to each building. But if we don't regionalize, we know how much money goes to each building. And the state kept the formula secret. So I told my committee members, look, I'm a mathematician. Every now and then this is useful. I will guess the formula. Or better yet, I will guess an approximation to the formula. And out of $3.5 million among 3 schools, I was within $10,000. And this is the power of mathematics. So the way we do this is using something called linear regression or the method of least squares. How many of you have seen this in a stats class or heard about this? All right, so we'll be covering that in this semester. It's one of my favorite applications of multivariable calculus. And so this is one of the big things I really want to do this semester. Most of you are not going to go off to math grad school and get PhDs. Some of you might, which is absolutely fine. I think it's a great career. But most of you are going to use math, hopefully, for something else. And I want to make sure we have time to really talk about how you use it. So the more you do at home, the more you post in terms of speaking up either in class or on the Google Sheet, the more this is going to fit what you want. If there are topics you want me to incorporate into class, let me know. I remember one year somebody wanted me to put in, I think, culinary issues involving honey. And so I'm up for a challenge. It was about this time that someone's phone went off in the first class. So the cell phone policy is as follows. Put your phone on silent. If you are expecting an important call, let me know, and then don't have it on silent. If the phone goes off once, anytime in the semester, it's a warning. If it goes off twice, the entire class has a quiz. Or the class can elect the Dunkin' Donuts policy, where if someone's phone goes off, they have to provide breakfast to everybody the next day. So I will let the class decide that at the time. Okay? So I'm not going to go through the mechanics as to how much things cost in great detail. There'll be, I think, 2 midterms. I will drop the lowest one. There'll be optional quizzes each week. If your quiz average would help your average, I will count it. If your quiz average hurts your average, somehow those scores will all be lost. Homework will be very frequent. You need to pass the final to pass the course, but if you prepare for class, that's 60% of your grade. Right. Any mechanics questions? Okay, one of the big things is always how much rigor to get into in a math class. I had a friend who was taking one of the advanced math classes a year behind me at Yale, my undergrad, who basically left and became an engineer after being told that he proved something was an integer, he proved it was 1/2. He didn't prove that 1/2 is not an integer. And he said, I'm done, I don't want to get to that level. So in a class like this, it's always a challenge. How much detail do you want to see? Things are not true because Williams has hired me or because I have a degree from Princeton. Things are true because I can show you they follow from agreed upon laws and agreed upon rules of logical inference. That said, which things do we want to prove in detail and which things are we willing to accept? Sometimes we're going to need results from real analysis. And this becomes a motivation as to why you should continue in mathematics and see how you make this rigorous. So how many of you have seen a proof of the fundamental theorem of calculus? Okay. How many of you could prove the fundamental theorem of calculus right now if you had to? Okay. This is how I tell if I am doozy after giving blood or something like that. If I can quickly give the proof, I can leave. If I'm stumbling for a little bit because I've been doing this for 2 decades, I need to lie down a little bit longer. I will be giving you a proof of the fundamental theorem of calculus. I will not be giving you the most general proof of the fundamental theorem of calculus. I will be making a reasonable assumption that is true about all the functions you're going to consider, and it greatly simplifies the proof. And I'll say, and if you don't like this assumption, if you want to do it in more generality, this is the result you need from real analysis. So I'm going to try to focus on stuff like this. I want to just start right now with Russell's paradox. Have any of you heard of Russell's paradox? Okay. So I'm from Boston. If you have trouble understanding my accent at times, just tell me, and I'll try to speak a little bit clearer. So the great Frege was writing a monumental treatise on set theory. And Russell then said, well, what about the following? So consider R to be the collection of all objects x in the universe, and the colon means such that x is not an element of x. Okay, most things are not elements of themselves. Are there any Eagles fans in the audience today? And I actually spent 7 years in Princeton, just outside of Philadelphia. So the Eagles are my second favorite team. I'm really looking forward to the Super Bowl. It's my top two teams. Let's say we're looking at the list of Super Bowl champions. Give me names of teams on the Super Bowl champions. I'm sorry? Patriots. And in fact, if this was a multi-set, we could list the Patriots many times, but we'll just list the Patriots once. Who else is in this set? Cowboys. Steelers. So there's a lot of teams, and there are teams that are not in this set. Is the set of Super Bowl champions a Super Bowl champion? Is the collection of teams that won the Super Bowl a team that won the Super Bowl? No. Most things are not elements of themselves. If you look at the set of integers, 1, 2, 3, 4, 5, is the set of integers an integer? No. Most things are not elements of themselves. Okay. So let's consider this set R. Anybody know a natural question you might want to ask about R? There's two natural questions you could ask. Any thoughts? Does R contain itself? So the wicked question is R empty or non-empty? Is there anything in R? And then better than that, is R an element of R? So is R an element of R? So what are the possibilities? Yes and no. All right? So there's two possibilities, yes and no. Let's do the yes case. So if R is an R, and this is so much fun to say with a Boston accent. So if R is an R, R is the set of all objects that are not elements of themselves. Therefore, since R is an R, R is not an R. There's no way they could ever caption this. Therefore, R is not in R. All right? Do we agree that if R is an R, since it's the collection of all things that aren't elements of themselves, R cannot be an element of itself? So there's no reason in even considering the second case, because it must be the case that R is not an element of R. Well, it's only 10:16. We've got plenty of time today. Let's explore the second case. What would happen if R is not an element of R? Well, R is precisely the collection of all objects that aren't elements of themselves. So if R is not an element of itself, that immediately implies R is an R. So we have the ridiculous situation that R is an R precisely if it's not in itself. Contradiction. What are we contradicting? We're contradicting that this is a set. It turns out you cannot just collect all objects that have a given property together and say, you're a set. Set creation is more subtle. Most of you are probably not going to be creating sets and foundations of mathematics. Why am I doing this? To alert you how careful we need to be in building our foundations. It is very easy to accidentally assume things and not realize you're doing so. This is why we have to prove things. Just because something works occasionally does not mean it will always work. Okay? So we're not going to do too much on set theory. We'll just assume sets behave, and we'll trust the mathematicians who have done their job and made sure that our book is built on solid foundations. But I want you to be aware of why are we spending time proving things. Because sometimes these things are false. Okay? So what I want to do now is I want to teach you essentially half of multivariable calculus in a minute. All right. Unfortunately, my children are 8 and 10, so the cultural references for my kids are not quite, I think, at your level. So I tried this last class. Does anybody watch Nick's The Loud House? Exactly. So my kids are still a little bit too young. From my childhood, I'm a big fan of like the 1980s and movies like The Three Amigos. Anybody ever watch The Three Amigos? All right, excellent. So does anybody have a stopwatch, preferably one with a seconds hand? All right. I'm going to teach you half of multivariable calculus in under a minute. All right. So we're going to do partial differentiation. All right. Tell me when you're ready. Oh, you already started it. I can still do it. Ready? All right. So imagine you have a function f of x, y of two variables. Then the derivative of f with respect to x is taken by holding y constant and differentiating with respect to x. And we write df dx for partial f with respect to x. Time? Yeah, 34 seconds. Oh, so I'm slipping. It should have really been under 30 seconds, but I'm getting old. That's half the semester. Let's do an example. All right. So let's say I give you the function f of x is 3x squared plus 7x. Then df dx, or f prime of x, what would that be? 6x plus 7. Let's say I give you now the function f of xy is x squared y to the fourth plus xy cubed. What's the derivative of f with respect to x? So I'm keeping y constant. So what would be the derivative of x squared y to the fourth, imagining y is a constant? 2xy to the fourth. And what would the derivative of xy cubed be, treating y as a constant? It would just be just y to the third. So that's essentially half the semester. Okay. Why are we going to spend more time than this? Well, there's a lot of questions you can then ask. If I take the derivative with respect to f and then the derivative with respect to y, is that the same as taking the derivative with respect to y and the derivative with respect to x? Does order matter? So what would you hope? If you could choose how mathematics were, what would you hope? That it didn't matter. You'd also hope the derivative of a product is the product of the derivatives, the derivative of a quotient is the quotient of the derivatives. Your hopes have been dashed, they've been crushed. By now, you should be just beaten down. But most of the time, it actually is true here. Most of the time, you can interchange orders. In general, in life, you have to be careful. Would you rather have $1,000 added to your bank account and then interest credited, or interest credited and then have $1,000 added? You'd rather have $1,000 added so that it earns interest on you. So I love Rubik's Cubes. I think Rubik's Cubes are great examples of a lot of things. This is a fun Red Sox Rubik's Cube. What I like about this is, unlike standard cubes, the sides are not monochromatic. And so if you look closely, and I'll put it on over here, you notice one of the B's is in a different configuration than the others. And the reason is, when this cube was solved, it was solved in such a way that I actually rotated the center square. If the sides were all one color, I would never have noticed that. The Rubik's Cube is a great object for order of steps matters. And what this means is that if you actually solve a Rubik's Cube, or if you think you know how to solve a Rubik's Cube, you might not actually know how to solve a generic cube. You might only know how to solve a monochromatic one. So we've got to be very careful. And so we're going to spend a lot of time trying to motivate why can we interchange orders. Another question is, what does it mean for a function to be differentiable? If my function is differentiable with respect to x, and if it's differentiable with respect to y, should it be differentiable? What would you like to say? Yes. That one is not true. You need the derivatives to be continuous. And so this is to just give you a sense of why we're going to spend so much time on differentiation. A lot of it is we're going to be reproving a lot of results from calculus. In calculus you have the sum rule, still holds. The product rule, still holds. These things propagate upward. They sometimes become a little bit more involved because you now have multi-dimensions and you now have vectors coming into play. But a lot of the rules continue. We'll prove an analog of the fundamental theorem of calculus. But it turns out if the two partial derivatives exist, that's not quite enough to prove that the function is differentiable. And so we'll have to worry about some issues like that. Okay, but in terms of just computing things, it's not so bad. I strongly urge you to get familiar with using computer programs. Mathematica is wonderful in terms of being able to draw things and visualize things. You should still be able to take basic derivatives and antiderivatives by yourself, but there are packages that do this for you. Check your work. Learn how to use them. They have wonderful graphing capabilities. Now, one of the problems I could give you for multivariable calculus is you have two cylinders. They intersect at right angles. They have the same radii. What's the volume of the region of intersection? Okay. How many of you are excited about solving problems like this? When I was a grad student at Princeton, I was given the curriculum to use. And I remember one year asking the students, so could you talk to me? What did you like? What did you not like? Did you like the problems like this? Okay. Should we remove them for the students next year? No, no, no. Why should we keep them? Well, we had to suffer. They should suffer. And then I just smiled and said, do you know how many years in a row I've now had this conversation? Because no one would be the one to break the chain. Well, fortunately, I'm the professor now. And so I'm not that excited about cylinders intersecting with cylinders and finding the volume or the area of stuff like that. They're good problems to do and know. And there will be times I will give you busy work problems just because you need to get the skills down. You need to be able to do the derivatives. You need to do the integrals. But I want to try to focus whenever possible on applying the mathematics to do things. And so if there are things you want to see, let me know. Okay? So we will have at least one lecture on applying multivariable calculus to baseball. So I've actually worked a lot with people in MLB. If you've read Moneyball or seen the movie, I've actually met a lot of the people there and have some very interesting stories I can say once there's a camera malfunction and things are not being recorded. And then I can't remember if I've said it, but the recording device is on me. So when you make comments, it should not really be detectable on the recording. Okay. So what I want to do now is I want to do some basic material you should have seen. How many of you have seen the Pythagorean theorem? How many of you could prove it? I should keep my hand up. Okay. How many of you can prove it more than one way? 2 ways? 3 ways? Okay. How many of you know which US president is credited with a proof of the Pythagorean theorem? One US president is given credit as having come up with an original proof. Yes, it is Garfield. We will not get into a discussion as to whether or not his trapezoidal proof is too similar to another one to truly merit, but he is credited with a proof. Anybody know how Garfield died? Nope, nope. He was shot. Where was he going? Williams, I believe, for his 25th reunion. So just to warn you, okay? Yeah, I'm just doing my due diligence. So I want to prove the Pythagorean theorem. All right? So Pythagorean, so A, B, C, A squared plus B squared is C squared. So the standard proof you often see is you drop down squares from each one of these and you show that the areas are the same and you divide them up in a lot of painful different ways. I'm going to show you a nice geometric proof and then I'm going to show you a very powerful dimensional analysis proof. And I really like the dimensional analysis because it gets to fundamentally why is it true. There are a lot of things where I can do long, tedious calculations, and when the dust settles, the result is true, and you can follow everything line by line by line. Locally, you know what's going on, and globally, you have no idea what's happening. There's a lot of math proofs like that. I want to try to do things that will build intuition and that you can then use to attack a variety of problems. So here's the standard nice proof. We will imagine I can draw well. So here is B, here is A. Here is B, here is A, here is B, here is A, here is B, here is A. And then these will be C on the inside. So I have 4 right angles in the corner. If this is theta, this is theta, this is theta, this is theta. What would be this angle over here? Yes? 90 minus theta. Excellent. And so if this is 90 minus theta and that's theta, what must this angle be here? 90. So in fact, we have a square inside a square. We're going to calculate the area of the square 2 different ways. One way is just as a big square, and the other way is as a square plus 4 triangles. So we need to know what the area of a triangle, of a right triangle is. What's the area of a right triangle with sides A and B? Y.
Because it's a rectangle, you divide it.
Excellent. So we start off as a fundamental notion that if we have a rectangle that's x by y, we're going to say its area is x times y. And then if we divide it in half, the two triangles are similar, and then we'll go through those arguments and say they must each have half the area. So we will assume we know the area of a rectangle, and from that the area of a right triangle. You can actually now deduce from this the area of any triangle. All right, so we get the big square is a plus b squared, and then we have the smallest square plus 4 triangles, which is 1/2 ab. So when we expand things out, we get a squared plus 2ab plus b squared is c squared plus 2ab. The 2ab's cancel, and you get a squared plus b squared is c squared. And we put in a filled box. This means QED, correlate demonstratum, that which was to be proved. We've reached the end of the proof. We did make an assumption. It's a really subtle assumption, but we made an assumption. The assumption is that if I take a triangle and I move it through space by rotating and translating, I'm not changing its area. It's a reasonable assumption, but it is an assumption. There is probably one of the strangest results in mathematics you will ever hear called the Banach-Tarski paradox. And it says the following. Take a sphere. Chop the sphere up into 5 very special, distinct pieces. So these are pieces that have nothing in common. So I've split it into 5 sets, okay? Take 3 of those pieces and translate and rotate them over here to the right, and take 2 of the pieces and translate and rotate them to the left. If you do your cuts properly and you do your translations and rotations properly, you then form 2 complete copies of the sphere with no hole. As an application, take a gold sphere. Take a stack of $100 bills. Double your money. This uses something called the axiom of choice. Certain people, myself included, we don't like the axiom of choice. This is one of the reasons I don't like the axiom of choice. It allows you to do stuff like this. The good news is the types of cuts you have to do are so bad they can't even be described. They cannot be done in the real world. But theoretically, some kind of partitioning exists. And so you always want to get a sense of what are you assuming when you do your arguments. Okay, this is the standard proof. We are, for the most part, comfortable with saying we will assume that as we translate and rotate, that does not change the area. But it does have some interesting effects later. All right. Any questions on this standard proof before we go to the dimensional analysis? All right. How many people have seen dimensional analysis or factor labeling from like a chemistry or physics class? Okay. It's extremely useful to add units to problems, and that gives you an idea of what kind of relationships there are. So I'm going to start by analyzing a pendulum as an example of the power of dimensional analysis. So here's my pendulum. So I have a rod of some length L. I have some initial displacement angle theta. I have the gravitational force G. And I have the mass M. And I want to calculate the period, how long it takes to go back and forth. So I have the period t, which is in seconds. And let's look at the quantities that I have in play. I have the length L, which is in meters. I have the mass M, which is in kilograms. I have gravity G. Anybody know the units for the acceleration due to gravity? Meters per second squared. And then I have the angle theta, which is unitless. So using these 4 quantities, I somehow have to get seconds. which is the odd quantity out? Which is the quantity that can have nothing to do with period? Mass. Because if I have mass, I have no way to cancel the units of kilograms. So without even doing anything in the lab, we predict the answer is independent of the mass. What's the only way I can get a unit of seconds using my length, gravity, and angle? So how could I get seconds? Square root of L over G. And then I can put in any function of theta. This method will not allow me to sniff out the function of theta, but without even going to the lab, if I quadruple the length, I should double the period. And it's amazing that we can get that much information before we do any calculations in the lab, before we do any experimentation, any measurement. So this is the power of dimensional analysis. What I want to do now is I want to apply this to Pythagoras. So this is one of the most important relationships we have. It's how we measure distance. So we measure distance by the straight line connecting. Now there are times when you can't always measure distance by straight line connecting. Can you give me an example of, if I want to know how far it is from one place to another, just doing the straight line connecting is not a good way to go? Over mountains, right? I'm not able to just tunnel through the mountain. I've got to go up the mountain and down the mountain. So almost surely this is a joke. I've never really wanted to investigate because I smile imagining that this actually happened. There are crimes for selling drugs near schools. And there are crimes for selling drugs. If you sell drugs within a certain distance of a school, the penalty is often higher. And so there's the story of somebody who was caught selling drugs, and he was within the critical distance if you measure it according to Pythagoras with a straight line connecting, but because this was being done in a city with city blocks, his lawyers argued, well, you can't go straight through like that, and if you go through the city blocks, it's actually outside, and he should be subject to the smaller penalty. And I don't really want to investigate as to whether or not, I just like to imagine the mathematicians presenting their arguments as to how distance should be measured to the judge. So I want to give you a dimensional analysis proof of Pythagoras. So we'll go back. Here's A, here's B, here's C. And I'll call that angle down there theta. And I claim that if I write the area as a function of the angle and the hypotenuse, it's got to be of the following functional form: f of theta times c squared. So what this means is if I double the hypotenuse, the area increases by a factor of 4. If I triple the hypotenuse, the area increases by a factor of 9. So when I was young in geometry, they talked about corresponding parts of congruent triangles are congruent, CP, CTC. Does that phrase sound even vaguely familiar? So if you think about what happens, if I double C, I'll also double B, and I'll double A. And since the area of the triangle is 1/2 AB, if I double A and I double B, the area goes up by 2 squared. If I triple A and I triple B, the area goes up by 3 squared. So does everyone agree that the area, the functional form, has to look like some function of theta times hypotenuse squared? Happy with this? Okay. How many of you remember doing geometry proofs? Okay. In a lot of geometry proofs, it always comes down to cleverly drawing an auxiliary line. And that's the hardest part, is figuring out where you should draw an auxiliary line. Well, we're doing a problem here on right angles. So right now we like right angles. Can anybody think of a way to draw an auxiliary line that will give me right angles?
From the corner with the 90-degree angle to the...
So if I draw like that, I get 2 new right angles. So I've now created 2 more triangles. I'm going to give them the very boring names of triangle 1 and triangle 2. If this angle is theta here, what's the angle up here? And if that's 90 minus theta, what's the angle over here? That must be theta. Or correspondingly, this angle down here is 90 minus theta, so that must be theta. So all of these triangles are similar. And we know the area of triangle 1 plus the area of triangle 2 is the area of the whole. Okay? What's the area of triangle 1? So what would be the area of triangle 1? Yes?
Function of theta in square.
A function of theta. Why?
Because
Because A is the hypotenuse. So for the big triangle, A is a side, but for the small triangle 1, it's a hypotenuse. What's the area of triangle 2? So what would be the area of triangle 2? Function of theta times b squared is function of theta times c squared. What do we now do?
cancel out function of theta.
And now we get a squared plus b squared is c squared. And there's Pythagoras. Is this step permissible? This is where you really hate being in a math class. Am I allowed to divide by f of theta?
Theta is 0. Or
If f of theta is not 0, this is a math class. You are not allowed to divide by 0. What would it mean for f of theta to be 0? There's no area. So the only way that would happen, okay. So we know f of theta is not 0, so we're okay as f of theta is not 0. But technically, you do have to note this. It's very easy to make mistakes. In fact, I find that over the years, it's the algebra that causes students the most issues. Often on exponents or on division and fractions. And if you have any questions about this, I'm happy to chat. So as a quick test of how people are doing, in lowest terms, what would be 16 over 64? A quarter, good. Let's give you a harder one, 19 over 95. Fifth, excellent. 49 over 98. Half. Okay, you guys are slowing down a little bit. 12 over 24, we'll do one more. Fourth. We got a fourth at 9 o'clock, although maybe we're just too tired. I'm getting a fourth. Am I the only one getting a fourth? Oh, crap. All right. This is where I'm upset that the camera is recording this, because this will be extremely embarrassing if I'm wrong. All right, let's see. 16 over 64, I cancel the 6's and I get 1/4. 19 over 95, I cancel the 9's and I get 1/5. 49 over 98, I cancel the 9's, that's 4/8, which reduces to 1/4. So the way you divide two fractions, if they're both 2 digits, with the same number on opposite diagonals, which is not the main diagonal, is you cancel them. And therefore, 12 over 24 must be 1/4. Okay, so obviously this is wrong. This is called proof by example. Proof by example is not a valid proof technique. There's proof by exhaustion. And the name should give you a sense of how often you want to use it. Proof by exhaustion basically goes as follows. Let's enumerate every possibility and show that it works in every possibility, and now we're done. So you can get a sense of, as the problem becomes more and more complex, just how likely you are to want to do proof by exhaustion. Just because something works for a couple of cases does not mean it will continue to work. That doesn't mean it's a bad idea to do special cases. You want to build intuition. The hope is that if things work for enough examples, usually if something works 3 times, you should start to get a little bit confident. Do you think these are 3 generic fractions? No, right? This is a well-planned lecture, right? Almost surely I prepared those ahead of time. Now what you might sometimes do is you might keep an example in strategic reserve. And so if people doubt that it's working, well, here, let me do another example. There's a great polynomial that has integer coefficients. It's a quadratic. And its first like 40 or 41 values are prime numbers. And so what you can do is you can give the first, say, 35 values and say, look, it's always prime. No, I can't believe. Well, let's do a few more. And you keep a few more in reserve. Eventually the pattern breaks down. That doesn't mean that you don't gather data, it just means you have to have a healthy skepticism of data. All right, so I want to end with an extra credit problem. So how many of you are interested in baseball statistics or applying statistics to sports? Okay, so I do a lot of work on that, and I have a lot of opportunities for students on projects like that. There's a really simple way of predicting who's going to win a game. So say A wins P% of the time, and B wins Q% of the time. Then I'm going to give you 4 formulas, and one of the 4 formulas actually does a pretty good job of predicting the probability that A beats B. It's P plus or minus PQ over P plus or minus PQ plus or minus 2PQ, where these two are the same. So there's 4 possibilities. Plus sign here, plus sign here, plus sign here, minus sign here, minus sign here, plus sign here, minus sign there, minus sign there. There are 4 cases. And I can even give you a probabilistic justification as to why this works. But imagine I tell you that a formula like this does a good job. Your goal is to figure out which of the 4 formulas is it. How would you try to figure out which formula works? What might you try? Any cases that might be worth exploring? Are there any cases where you should know the answer?
If P or Q are 100 or 0.
Okay, so can somebody give me a football team that might be useful here? Who knows the football season from this year? What team am I thinking of? The Browns, right? How many wins do the Browns have this year? 0. They actually did worse than their previous year when they had 1 win. So in the last 3 years, the Cleveland Browns have won 4 games. If you look at their average wins per year, the closest integer is 1. So for the Cleveland Browns, their winning percentage is 0. If a team plays the Cleveland Browns, what would you predict?
They win.
As long as it's not the Cleveland Browns playing themselves, it's like an intra-squad scrimmage. So if you take Q equals 0, what should this formula predict? It should predict A wins. So you have some idea of special cases. And then can you think of other special cases where you can then use to try to figure out which one of these might be true? So we have time to do one more special case. Can anybody think of another choice of values for P and Q? Okay, so if P equals Q equals 1/2, what should you get? 1/2. Could you do it a little bit more generally? So I'll leave you to think if you can do this a little bit more generally. Years ago, on a very old primitive Apple baseball game, my brother and one of his friends created their own players. And my brother created the perfect pitcher who always strikes everybody out. And his friend created the perfect hitter who always hits a home run. And they faced off. And the computer hung for several minutes trying to figure out what the hell it should do in a situation like this. What situation do you think might be similar in this case?
If both are 100.
If both are 100, if both are 0. What if the Browns play the Browns? They always lose, but they're playing themselves. So what should the formula give you in this situation when the Browns play the Browns? So the computer, my brother and his friend thought the computer had actually crashed, but it finally returned a result for the perfect pitcher facing the perfect hitter. And if you think about it, it actually does make sense. Anybody want to conjecture what happened? Pitcher always strikes out at the batter. Batter always hits a home run. What was the result? It was a double. The computer finally said, look, average batter, this batter normally gets 4 bases. Pitcher normally allows 0 bases. I'll give you 2 bases. It's not bad. And it's an interesting warning that when you're building something, you want to make sure that if people do something strange, your system doesn't crash, that it has a way of providing an answer. Even if it's not necessarily the best answer, then it just provides an answer. All right, so this is a good place to stop. I will stick around for a couple minutes if anybody has any questions. If you haven't the handout yet,